So this week we're going to talk about logistic regression and neural networks. We're also going to talk a little bit about PyTorch. So continuous and discrete data. Um, these two forms of data are different in a lot of very important ways. One, usually with continuous data, you assume that there's a relatively normal distribution that can take pretty much any value. And that's just not the case for discrete data. In discrete data, you have to think very carefully about the assumptions your model is making in terms of what values can come out of it. If the only values in your data can take are 0 and 1, you don't want a model that produces -1, you don't want a model that produces -2 or positive 1.5. Discrete data is also very different in that you're working with a PMF, not a PDF. So there is, in continuous data, there's kind of an assumption of continuity in the distribution function. So you can take integrals. You can do a lot of things that are a lot easier. With discrete data, that's definitely not the case. So in terms of what assumptions of the model get violated with discrete data, the assumption of normality is a big one. If you're ever making the assumption of normality, also you have the important assumption that the error is normal 0 sigma squared, and that's usually not an easy assumption to make when you have discrete data. So what models work with discrete data? Neural nets work very well. Anything with classification works much better with discrete data than regression algorithms. Neural networks revolutionized the field of machine learning. At their heart, neural networks are an easier way to fit a function with a massive amount of data. You wouldn't think that fitting a function, you wouldn't think that coming up with a better way to fit a high-dimensional function would be that important. But it turns out that this is an incredibly useful task for games, computer vision, natural language processing, chatbots, and so many other things. Neural networks have been slow to be adapted in economics. Does anyone have any ideas as to maybe why it's taken so long? Why is our field not moving faster to adapt something that has been, kind of revolutionary in many other fields?
I think it has to do with something that you mentioned at the very beginning of the semester, and I think you asked like why like economists are like more suitable for like doing machine learning rather than like let's say and like casual like typical software engineers. And I think what you said is that is because economists know how to interpret like data, like
Mm.
so I think, and like you said, neural networks, they're mostly good for discrete data, right? So
So neural networks you can use with continuous data,
right,
but
right.
yeah, you're on the right track though. Absolutely.
Yeah, so like yeah, so I think it's mostly because of the fact that economists sort of already know how to interpret like various types of data, like sort of intuition. So but I guess yeah, I guess neural networks would be better, like will definitely make it like um easier for them to analyze the data. But I think but I just sort of like what I think like it sort of ties back like to the question that you asked in the like
Mm-hmm.
very beginning of the classes of why do like people hire economists to do machine learning rather than like software engineers or other engineers.
Yeah. So economists are very focused on causality.
Right.
Um, and neural networks are really great for prediction, but they're not as good for causality because we don't really know exactly how they work. Further, most problems in economics are not really big data problems, they're more medium data problems. So tools like neural networks aren't as useful when you have other very useful tools like logistic and regular regression that work very well. Further, there's just an inherency bias where economists have certain tools they've used for a long time, so why shift to these new ones? The causality problem in neural nets is not unsolvable. A lot of work is being done to create explainable neural networks, and that I think is a big push in the future, is creating versions of neural networks that also can be understood by researchers and can be used for things like hypothesis tests. Currently, in economics, neural networks are most used for labeling data and handling unstructured data. If you have image data or if you have language data, this is a great way of dealing with it. They're also very common in dynamic fields like macro and IO. So I don't know if you've taken macro, or if anyone on the call who will be listening after has taken macro, but macroeconomics is fundamentally about dynamics, and dynamics is usually solved by solving a dynamic value iteration problem. And the way you do that is you effectively map a high dimensional function. And neural networks make that process much easier. So we're seeing a lot of movement towards neural networks in macroeconomics and IO. And obviously, more applications are coming. This is still a nascent field. This isn't a well-developed field by any means. It's still growing. So why can't you use a linear regression for a discrete variable? You're going to end up with values that are not between 0 and 1. And you're going to find out that the assumptions of the linear model are invalidated. With logistic regression, one of the interesting things is that effect sizes change as output increases. So with a linear regression, you kind of get something that's like this. And so there's maybe you also have something like this or something like this if you're doing a polynomial regression, but normally you end up with something with a relatively fixed effect size for the entire domain of the variables. With logistic regression, you get something that ends up looking like this. So you can think of this line at this point as p equals 0.5. So all of this over here is the probability is greater than 0.5. All of this over here is probably less than 0.5. And right here, where it crosses the y-axis, that's when probability is exactly equal to 0.5. If you'll notice, it's really flat over in this region. It's really flat over in this region, and it moves really quickly over in this region. So you can think of this as probability can only be between 0 and 1. And when the probability gets beyond a certain point, it kind of levels off, and it's effectively going to be 1. It can't happen, but at a certain point, it's very difficult to provide additional information unless you have tons and tons of data. And even then, it's very difficult to discern between an observation that's 90% likely to do something, and an observation that's 95% likely. So effect sizes are not constant with output, unlike in linear regression, where if you increase the output, the effect size remains basically the same. What else differentiates them? linear regressions can usually be solved analytically. It's very difficult to solve most logistic regressions analytically. You can usually think about, and this is where the recent stuff with gradient descent comes in real handy. The metaphor I like to use for how you do logistic regression is you have a hill that kind of looks like this, and you're trying to get your ball over there, and you're starting maybe someone here. So you go down, then maybe you go back up, and then you go down again, you go back up, and hopefully eventually your ball goes down here to the local minimum, or to the global minimum rather. So hopefully you run the logistic regression and you get to a global minimum and everything's great. But when you run a linear regression, you can pretty easily just minimize a function. So there are really two answers to this question. So this is a sigmoid function. The sigmoid function, this is a univariate sigmoid function, but it'd be pretty easy to adjust to a multivariate sigmoid function. The sigmoid function is, and a good way of thinking about it is as a mapping function. So you have a bunch of values, Z1, Z2, Z3, Z4. You have a bunch of values, and you need to map them to this area between 0 and 1. So you could have, you have a bunch of possible probabilities, and you need to map it to something in this range. In particular, you could do this with just some value of one probability between 0 and 1, but you can do it with many probabilities of many different events with what's called multinomial logit. So really what sigmoid function does is maps a set of data to 0 and 1, or to between 0 and 1. So it's really about scaling the data. So so we have Z underscore J here. If Z underscore J is, as Z underscore J goes to infinity, let me write that limit better. So the limit as Z underscore J goes to infinity, what do you think that is? Of sigma Z underscore I. What do you think that limit's going to be?
Hmm. Would it be like closer to 1 or
Yeah, exactly.
okay,
So
okay.
this function sigma underscore zi is decreasing. It's strictly decreasing in z underscore I.
Right.
So the higher z underscore j goes, which is, yeah, z underscore j is just the output of your regression. The higher it goes, the more likely an event is. So as z underscore j goes to infinity, sigma goes to 1. On the other hand, what happens as z underscore j goes to negative infinity?
Then I guess it'll be the opposite. It'll be closer to 0.
Yeah, as z underscore j goes to negative infinity, sigma z underscore I goes to 0. All right. So now, when does this equal 1/2? When will this equal 1/2?
That's a good question. Would it be like
So let's actually just solve it right now. We've got time. So 0.5 equals 1 over 1 plus e to the negative z underscore j. 0.5 times 1 plus e to the negative z underscore j equals 1. 2 equals 1 plus e to the negative z underscore j. 1 equals e to the negative z underscore j. So what's the last step to get to solve for z underscore j?
Natural log.
Yeah, we take the natural log of both sides. And what's the natural log of 1?
0.
0. So the limit as z underscore j goes to infinity is equal to 1. So this is strictly increasing in terms of z underscore j, but it's increasing very slowly towards 1. And then the limit as g underscore j goes to negative infinity is 0. And then the value of sigma of z underscore I equals 0 equals 0.5. So as you become more and more likely to do something, as the logistic regression becomes more and more likely to predict that you do something, the sigmoid function goes towards 1. On the other hand, it goes towards 0. On the other hand, it's never going to reach 0 because it's never going to say that you're not going to do something. And then at 0, it's perfectly in between. Why would it be a bad thing if the logistic function, or why would it be a bad thing if logistic regression outputted a 0 or 1? If it said that the probability was 0 or 1? Why is it a good idea to have an output with a probability that is between those, but is never exactly equal to one or the other?
I guess it has to do with like the predictability of it, perhaps.
Exactly. So you don't want to have a model, and this is not just true in terms of logistic regression, it's true anytime you build a model. You never want a model that can produce a prediction that's falsifiable by your data. You always want a model, when you're doing prediction, you always want a model that can, you give it data and the model will always say that the data is possible. You don't want the model to say, oh, this data is impossible, because that's going to break your model. And there are people who run models, and those models are made on bad assumptions, and then they get data that falsifies those assumptions, and then the model just breaks. So it's very important when you're thinking about building a model is to think about what would break my model and how do I make sure that doesn't happen. So this is the softmax function. So this is basically the multivariate portion of the sigmoid function. So the nice thing about this one, so whereas the sigmoid function divided one space between two different types of probabilities, this one will divide a space between n different sections of probabilities. So that's a really nice thing. And the nice property that you find here is that for so when you have e of z underscore I over sum j equals 1 to j of e of z underscore j, what you end up with is that e z underscore I, you can actually break down this in the bottom into e of z underscore I plus sum from j not equal to I to j of e to the z underscore j. So this gets to one of those things where actually this is always less than 1 and it's always greater than 0. So it's less than 1. It's always less than 1. It's always greater than 0. But importantly, you have the ability for it to be able to tell for a variety of different possible classes which one is more or less likely by the fact that E underscore ZI, you're not even really comparing it to any other individual class. You're comparing it to how big it is compared to the rest of the potential classes. So this is a very important function. It's used all the time in neural nets. And basically what it does is, like I said, maps from a continuous space to a discrete space. And it allows you to take a bunch of different data and turn it into probabilities by class. So now let's talk about the steps you would need to do to perform a logistic regression. First off, you randomly initialize weights. You start off with weights equals NP dot zeros, and then parameter size. So you want as many weights as parameters. So in case of linear regression, your weights are your betas. So you want as many weights as parameters, and you want to randomly initialize them. This was actually a bad initialization. It's not that bad because in theory, NP.0 is going to be your median or your average of your a priori values for your predictions of your parameters. But in actuality, if you want to run a little bit better, and the reason why you don't use NP.0s when you're randomly initializing parameters is because if you use NP.0s, you're more likely to get stuck at a saddle point or something. What you really should do is weights initial equals np.rand and then parameter number. So you're creating a random matrix centered around zero you're taking a random matrix centered around zero of your parameters. And then you do weights in this. Take the dot product of the initial weights and your data. So the weights times your data. So that, if we go back to the previous one, that is, go back to the previous slide, that's this xi times beta. So you take the dot product of your weights and your data, then you take the log likelihood. So the log likelihood is basically you find the probabilities that you're saying it is, and then based on the probabilities that you're saying it is, so the probabilities, let's remember, are this right here. So you can think of this as P of xi. So this softmax, this sigmoid function gives the probability of a particular observation. And then what you're doing is when you're running logistic regression is you're taking the log likelihood. So you know the likelihood function you've given, which is the logistic likelihood function. And then you multiply the applied probabilities that you get for all your xi. And then this gives you, and you of course take the log of that. So it's really just sum because remember, when you take the log, you go from a multiplication to a sum. So it's a sum of log p of xi. And then you now find the gradient of the log likelihood function. So you take d beta I, d your weight, d, or sorry, let me go back. You take dli over d beta I, and then that gives you your gradient. And then now you perform gradient descent. So beta t plus 1 equals beta t plus alpha delta t. So your gradient times, or excuse me, sorry. I meant to say minus alpha delta t. So your gradient times your learning rate subtracted from your weights is equal to your next weights. And you keep doing this until you hit convergence. So if we write this up in pseudocode, it would be wall not converge. And then let's say we initialize the weights here. So we've initialized the weights, and then we've initialized a second set of weights. So weights 1, weights 2. And then, so what you want to do is the wall weights 1 minus weights 2 greater than epsilon. Epsilon some small number. And then, so you initialize weights 1, weights 2, and then wall not converged. And then you find the probability, find log likelihood, find gradients, step, and then you repeat until you've converged. So that's logistic regression in a nutshell. And then, so this is the likelihood function. Logistic regression actually has a relatively beautiful likelihood function. Logistic regression has a likelihood function that is just the probability of y equals 1, given your data, raised to yi times the probability of 1 minus, or times 1 minus the probability of y equals 1, given your data, times 1 minus yi. So the nice thing about this is that this yi will either be 1 or 0. So if this is 0, this becomes 1. If this is 1, this becomes 1. So this is either going to reduce to probability of yi equals 1, given that y equals 1 times 1, or it's going to reduce to probability yi equals 0, which is the probability 1 minus yi, or 1 minus probability y equals 1 raised to the 1 times 1. So that's a really beautiful thing, is one of these terms is going to go to 1, and you only have to worry about the other one. So log likelihood here is just yi. Remember, 1 or 0. So one of these terms is going to go to 0 times log of pi plus 1 minus yi times log of 1 minus pi. So, and then the final thing we want to do with this log likelihood before we move on is we want to normalize it. Why do we normally, first off, why do we divide by n here? Why I divide by n on this log likelihood function?
Not sure, to be honest.
So let's say we just did this. That'd be great, but there's a problem here. What happens if we add more observations? Is this going to go up or down?
Uh, Up.
Yeah, mathematically, because it's a likelihood function, it has to increase as you add observations. So this is going to go up as you add observations. So you're penalizing models that add more observations. That's not really a great idea. You want to be able to compare different models with different number of observations on the same terms. So that's why you divide by n, is so that now you have a normalized log loss or log likelihood. So now if n is 100 or if n is 10, it means the same thing because it's normalized by the number of observations. Now, why do we take a negative here? That's kind of a strange thing. Why do we want to take a negative when we do this in code?
Is it because one side of the equation would be too big and you're like
Now, that's a great question. That's something you often have to do. That's actually why we take the log here.
okay, okay,
That's
okay.
a great point. So we take the log partially because when you're dealing with these, let me see if I can go back. When you're dealing with these, functions right here, like this function gets really big. You're raising e to something that's a big number. Those functions get really big, and that can become problematic for your computer.
Hmm.
It can be problematic because the computers can only handle numbers that are so large, and if it becomes larger than that, the computer breaks down. It's also problematic because uh, it slows your computer down to be dealing with so many of those large numbers. You know, you have to store it, and that reduces memory. That's why we take the log. That's a great guess. The reason why we take the put in the negative here is that because we want to min, not max. So most algorithmic routines are written to minimize something because it's easier to minimize a convex function than to maximize a convex function. So we want to no, sorry, we want to maximize, not minimize. I'm sorry. Sorry, let me go back. We take the negative, oh yeah, no, we want to minimize. So we take the negative because we want to minimize, not maximize, because most functions are written to minimize, not maximize. So we want to maximize the likelihood function, but in order to do that, we have to minimize the log loss. So that's why you take the negative in these cases, is because it's easier to minimize something than to maximize something, even though what we know is that they're the same thing computationally. It's just that one is how we normally do things. So minimizing something is the same as maximizing the negative of it. So how would we find the gradient of log likelihood? Or log loss, rather. How would we find the gradient of this? Well, first off, what are we finding the gradient with respect to?
J, I would say J.
Well, we're
J,
finding the gradient of J with respect to something. What are we finding the gradient of J with respect to?
with respect to beta.
Yeah, with respect to beta, in this case, P, right?
Okay,
Sorry
right.
about that. My lights have gone off. Uh,
Is it one of those automatic lights that just goes off randomly?
Yeah, they go off multiple times throughout the day. Um, Economics department, man. So I find the derivative of this with respect to beta or with respect to P. And the way, what's the derivative of, so the really cool thing about the fact that yi is equal to 1 or yi is equal to 0 is this derivative, one of these will also go to 0. Because the derivative is equal to yi over p. The derivative of the log is 1 over n, and then plus 1 minus yi over 1 minus p. And then this is either going to go to 0 or this is either going to go to 0. One of these two is going to go to 0. And then the gradient, I don't know whether I took the gradient of the log likelihood or the log loss, but the gradient with respect to any beta is equal to negative yi minus y hat over times xj. I'm not going to get into this derivation right now. I think I have it later, but the cool thing is this gradient, if yi equals 1, this becomes 1 minus, if yi equals 1 and predicted y hat equals 1, it's become 1 minus 1 equals 0. And so so that's the gradient of 0. So what is that? So if this is 0, what happens in gradient descent?
So if it's 0, wait, trying to think. So okay, never mind. Cause I was thinking of the sigmoid function where we said like if it goes to 0, then technically it's between 0 and 1, which is like 0.5. So I was wondering if it's the same case with this or not.
So no, in this case, if this gradient is equal to 0, and let's say gradient of j with respect to beta is equal to 0, beta j is equal to 0 for all beta j, all j. In that case, the gradient is equal to 0. And remember, gradient descent is beta j t plus 1 equals beta j t minus alpha times gradients. Gradient's right there. If this is equal to 0, beta j t equals beta j t plus 1, and your algorithm converges.
Okay.
So if you're predicting everything right, and this is right for every single observation, your algorithm converges because gradient 0.
Interesting. Okay.
So probit is a more generalized form of logit. Probit assumes a normal standard error, while logit assumes a logistic standard error. Logit is preferable for data science because it's a closed form solution. It's much easier to solve logistic regression. With probit, you tend to have to calculate a use simulation to calculate a value of the normal CDF, which is not something you want to do. But Probit is a useful thing to do because it's much more general than Logit. Whereas Logit assumes a very specific standard error, Probit assumes a very general standard error, but it's much harder to solve a Probit regression than a Logit regression. So at their basic level, neural networks consist of linear regressions followed by nonlinear activation functions. What we just talked about with logistic regressions, those are technically neural networks. Neural networks are not at all different from logistic or linear regressions. It's just that we're chaining a lot of them together and we're adding these nonlinear activation functions. So we start off with it was essentially logistic regression, and then we add multiple layers, special functions, and nonlinearities, and then suddenly we get to this thing that's way more powerful. So just to review gradient descent, this is what we've been talking about all session. You have the ball, you want to push it down the hill. You're updating a little bit at a time based on your gradient. When this gradient is 0, W new equals W old, and then your algorithm terminates. Usually you're not going to get to 0, so you're just going to do when W new minus W old is greater than epsilon in absolute value, of course. So forward propagation. So neural networks have 2 different steps. The first one is forward propagation. So forward propagation, you can think of it as you're pushing the data. You have inputs, and then you have outputs. And forward propagation is how the data goes through the network to get from input to output. So the most basic form of a forward propagation is just a linear regression. So with linear regression, you have a set of betas, and you do x beta equals y. With a neural network, what you would effectively do as linear regression is you would have your input x, you would multiply it by weights beta I, and then you would just have an output is y, and then you would take an analytical minimum of the mean squared error. So fundamentally, a neural network is an extremely basic kind of linear regression. And so, a linear regression is an extremely basic kind of neural network. So you can add other layers and you can make it more complex, but the basic level, you're just, all you're doing is you're doing x times beta, your data times the weights, and then you're putting that through a activation function. So this is nonlinear, but does something to this, and then you're feeding it to the next layer where you're also, so this becomes your y, and your y becomes your x in the next layer, and you multiply it by different beta. So you're doing a series of linear regressions punctuated by nonlinear activation functions. So each node can learn from one particular feature of the data set. So that's the value of multiple layers. Is we talked about recently dimensionality reduction. Do you remember that last week, MD, when we talked about dimensionality reduction?
Yeah, I remember that.
That there are all these dimensions. This is what neural networks are really good at. This is what makes them spectacular, is we have a dimension that's really these values plus each other. Well, the neural network picks that up, and it will say, we have these nodes, and then these nodes all feed into this one node. So each of these nodes, and there can be so many of these, each of these nodes is a dimension of the data. It's picking up special relationships in the data. So as you add more and more and more nodes, you add more and more and more layers, each node's a dimension, and you can have dimensions made up of lower dimensions of the data, and slowly but surely you have this thing that's more and more complicated and more complex, and we don't know how it works. Well, we know how it works, we don't know like exactly what's going on. You end up with something that's able to pick up really complex representations of the data. So different layers learn different types of information, and different nodes learn different features of the data set. And then successive layers learn combinations of different features in earlier layers, and they learn more interesting patterns in the data. So activation functions create nonlinearities between layers. Without an activation function, there's not really anything interesting about a neural network. But when you add an activation function is just a nonlinear function between two layers. A good example of an activation function is softmax. What we saw earlier is an activation function. Usually that's the end of the neural network. Another good example of an activation function is something called ReLU. So it's 0 if it's less than 0. So it's 0, it's less than 0, and it's 1 if it's x if it's greater than 0. So f of x equals x greater than 0, and 0, x less than or equal to 0. So that's ReLU, rectified linear. And I'll show you this in a moment. But without activation functions, you're effectively not doing anything interesting. Activation functions allow you to take very interesting combinations of data, and allows you to see exceptionally interesting patterns in your data. So here we go with activation functions. You see sigmoid, which is just basically logistic regression. You see leaky ReLU, which is like ReLU, but it's just it's a little bit leaky, so it goes down slowly, but not all the way. ReLU and leaky ReLU are really useful because they allow you to, they solve the same problem that you have with that e to the z, where that goes to infinity and then your computer can't handle that. If you have ReLUs, you're going to effectively send some of your observations to 0, and your gradients aren't going to get huge. So actually, interestingly enough, what is the derivative, what is the gradient of ReLU? So the function is x if x greater than 0, and 0 if x less than or equal to 0. So what do you think the gradient of that is, MD?
Could you repeat the question?
What's the derivative of this function?
Okay, so we have x if x is greater than 0, and 0 if x is greater than or equal to 0. Well, the derivative would be just for x, it would be just 1.
Correct.
And
so the derivative of this section is just 1.
right.
And then the derivative of this section is just 0. And then
0, yeah.
exactly, it's mapped at 0. It's a discontinuity, so the gradient is undefined. So when you're coding
Okay.
this in reality, you usually code something where, like, you say if the derivative is 0, if it's exactly at 0, the derivative is just 0. So usually you hard code that. But right here, you have this thing that's very easy to take the derivative of, and it will send a lot of your observations to 0, which makes it really easy to work with. So these are activation functions, and allows you to learn really complex patterns in the data. So automatic differentiation is another feature in neural networks. So normally when you're doing logistic regression, or you're doing linear regression, you take the derivative manually. And when you've been optimizing things late in this class, you've been taking the derivative manually. But automatic differentiation replaces manual differentiation with a network graph that automatically finds the derivative, of a set of observations. Everything is chain rule. When in doubt, chain rule. So let's see if I have it. Yeah, so I have a network graph here that kind of shows how automatic differentiation works. Now I won't get too into it, partially because we're running a bit late, but partially also because I think I have a demonstration later, but you have a bunch of different operations, and you have A, it's directed acyclic graph, so there are no cycles, and so you have dc to EA, and then you'd have dc to W. So A dc is just equal to dc, or sorry, it's just equal to, or sorry, dA dW1. Let me go back for a moment. dA over dW1 is equal to dA over dB, dB over dW1. So right here we have AdB, and then we have dB dW1. And then you can take this all the way back, and you're just at every step, you're multiplying the derivatives, and that's chain rule. So just a reminder, chain rule is f of g of x is, or d over dx of f of g of x is equal to d f of g of x over dg of x times dg of x over dx. So that's just chain rule. And so ultimately you end up being able to calculate derivatives automatically and just multiply them together. And so that is something very useful for what's called back propagation. So I talked about earlier how forward pass is you're moving forward through the network. Backward pass, you're moving backward through the network. So you've already calculated everything. And so now you have your result. You have your result, and now you send it back through your network to get your derivative. So you get the derivative of the cost function with respect to each of the weights. And this allows weights and bias to be adjusted based on their impact on the cost. Back propagation is an incredibly special, beautiful thing in neural networks. So we have this output layer, and then we have each of these hidden layers. We have these input layers, we have these hidden layers, and we have this output layer. And then back propagation, you're multiplying all the way back here. You're multiplying to get the gradient, and then you're just doing a simple gradient descent. Usually, actually, with neural nets, you do a stochastic gradient descent, but you do WT plus 1 equals WT minus alpha, and then gradient. And what's special here is you're just doing this for thousands upon thousands of weights, and you're optimizing this model for thousands upon thousands of weights until you have something that fits the data really, really well. And this is a huge step forward for so many fields, because you don't need to know what it's doing. You just have to optimize over all of these different parameters until you have something that fits the data really well. Logistic regression is actually a type of neural network. I think I've said that a few times before in this class. It consists of one linear layer followed by a sigmoid activation function. So that's what we saw earlier tonight. That's actually a form of linear, a neural network. Many early neural networks utilize a simple multi-stage linear regression. It was actually believed that back when they were called multi-layer perceptrons, it was believed that neural networks could not work. It was impossible for them to work because people didn't realize you could add more and more layers. But as you added more and more and more layers, they became able to solve more and more complex problems. And then they became really the default for many problems today. So the output of the neural network is based on the last layer, the final activation function, the cost function. So you need to think about, when you're choosing a cost function, you need to think about what kind of problem is this? Is this a classification problem, which I should be using something like cross entropy loss? Is this a regression problem, which I should probably be using something like mean squared error? What is the implication of having mean squared error rather than mean absolute error? So the cost function will directly affect how your neural network learns to figure data. The number of output features is the last linear layer. Of the last linear layer is the number of features the input to the final activation function. So if you have, because remember, this is all done via matrices. So if you have something that's x comma y as the output features to your last linear layer, then that matrix is going to let's not use x comma y here. K comma n, because this is a matrix. F of k comma n, which is going to have dimensions k comma n. So the output features of the last linear layer is the number of features of the input of the final activation functions. So that's why you'll often see in the last linear layer, you'll have something that's 1 comma k, where k is the number of classes. So what you end up with is you multiply something that is n, where n is the number of observations, by 1 by k, and then you get an output that's n by k, where k is the number of classes and n is the number of observations, and you'll get, when you put this through softmax, you'll get a series of probabilities for each class. So that's something that's really cool within neural networks. Yeah, so if you ever get a chance, look into neural networks, they're the best. Some activation functions allow continuous variables. Others, like softmax, are really discrete. Which cost factions should you use for logistic regression? I'll just answer right here. You should use soft entropy or cost entropy loss, or basically what this loss function is it was independently discovered by computer scientists and probability theorists, but this is the normalized log loss of the logistic regression, and this is actually what you use as your loss function in a neural network when you're doing classification. So you just use the same thing that you use in logistic regression. And that's pretty much all classification problems is what you're going to use that. And then some activation functions will allow for continuous variables as outputs. Some, like softmax, are discrete. So if you feed in softmax, if you feed it into softmax, you're going to get probabilities output. So you might not want softmax as your last layer, as your activation function, rather. Which cost function should you use for logistic regression? Which cost function you use for continuous variables? For continuous variables, you should use mean squared error almost all the time. I'm not really going to get into transformers tonight. Just if you're interested, look them up. This is the T in ChatGPT, generative pre-trained transformers. And this is a step forward in neural networks. It used to be believed neural networks couldn't really solve language, and there was a barrier to solving computer vision. But by adding in an encoder and a decoder layer, and adding in what's called attention, which I won't get into tonight, you can solve a lot of very important problems that stop you from being able to use neural networks in these complex settings. So finding the gradient of the softmax function. So this is the softmax function. So to find the gradient, we take the derivative with respect to the weights. So this is, we rewrite the softmax function to start off with. And then to find the derivative with respect to zi, we basically do quotient rule. So this is squared. This is your bottom squared, and then this is your first time or bottom times the derivative of the top minus the top times the derivative of the bottom. So it's just quotient rule. And then I'm not meaning to be drawing there. And then what we do is we can rewrite this as e to the zi, so that's this right here, over e to the zi plus k does not equal I, e to the z k. So we're just factoring this out from 1 into 2. So we're factoring this out into 2 of these. And then we're factoring 1 out here. We're factoring 1 out here. And then we're moving this and this. We're factoring this out and moving it here. And then this minus this is both multiplied by e to this ei. And that becomes this. And what's really cool about this is that this right here is this. So that's just SI. And then this right here is 1 minus SI. This is the result I showed you earlier tonight, that the derivative of the softmax function is SI times 1 minus SI. It's the derivative of the softmax function is the softmax function times 1 minus the softmax function. It's a very easy to find gradient, and it makes things so much easier. So now let's talk about creating OR with a singular linear threshold neuron. So we want to use this to create OR. So we know that it's 1 if W transpose X plus B greater than or equal to 0, and 0 W transpose X plus B less than 0. And so OR means that if we have a truth table here, if we have X1 true and then X2 true, then it's true. If X1 is true, X2 is false, it's also true. And then if X1 is false and X2 is true, it's also true. It's only false if both X1 and X2 are true. So we have X1 and X2, and we want to create OR. So W1 times X1 plus W2 times X2. We want this to be greater than or equal to 0 if either one is true, and we want this to be less than 0 if X1 or X2 is false. So what do you think we can do here? What can we set W1 and W2 to here to recreate the OR gate?
Uh, hmm. could you repeat just one more time? I'm sort of like trying to rethink.
So we want something that's equal to that's greater than or equal to 0 if x1 or x2 is true. So if x1 or x2 is true, think about it as x1 equals 1 or 0. And if x1 or x2 is 1, we want it to be greater than 0. Otherwise, if both of them are false, if both of them are 0, we want it to be less than 0. So we're choosing here, we're choosing W1, which will multiply by x1. We're choosing W2, which will multiply by x2. And we're choosing
Right.
B, which is our bias. So our bias is our intercept in linear regression.
Okay, so it's almost like a truth table, basically.
Exactly.
Okay. So the question is which combination to use if we want like for
Yeah,
an OR gate?
what's a combination we can use if we want an OR gate?
So again, just to I'm sort of like losing like I sort of lost some stuff. So x1, so if x1 and x2 are both true, then we have uh greater than 0. Like
So if both x1 and x2 are true, we get 1. We
okay,
want
right.
an OR. So this is only 0 if both x1 and x2 are false.
Right. So for an OR gate, either x1 is 1 or x2 is 1. Either one works, right?
Or x1 and x2 are 1.
X1 and x2 or 1.
Either both are or just one is.
Yeah.
Yeah. So what should we let's start off with B. What do you think is a good value for B?
Hmm.
Let me say I give you B equals -1. So now what would you set W1 and W2 to here?
Okay. So okay, but what would so are you saying then x1 and x2 are both 1 here?
Yeah. Or sorry,
Okay.
W1 and W2 are both 1.
Okay.
So B equals -1. And then if x1 is 1, then and x2 is 0, then this will just become 0. This will become 1. -1 equals 0.
Right.
If it's both 1, then -1 will equal 1, and it'll be greater than 0.
Right.
So that's a neural network. That's a single layer neural network, and that's one way that this can work. What about an AND gate? So now we need a W1, W2, and B such that it's such that it only is true if both x1 and x2 are 1.
So
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 what's
it would be greater than 0, right? The entire thing would be greater than 0 still.
well, we want something such that if both x1 and x2 are 1, it's greater than 0. And if not, if either one is not 1, it's 0. Or less than 0, right? It's less than 0.
Hmm.
So I'm just going to give you bias because we're running out of time. Bias equals -2.
Okay.
And then what might we set the weights to?
So we already know that x1 and x2 are both 1,
Well,
right?
they can be both 1. So if they are both 1, what would be weights that would make it equal to 0?
So if both of them are 1, then both of the weights should be 1 as well, right?
Yeah. And so what happens if they're both 0 though?
Huh. Well, then it would just be less than 0 regardless of what
It'd
we
be
put.
-1, exactly.
Right, right.
And then what happens if one is 1 and the other one is 0?
Well, in that case, we have -1, right? Exactly.
Exactly. So that's how you create an OR gate with a single neuron.
So would it be fair to say that neurons basically have this follow the same structure, well, not structure, but like same idea as logic gates, where you have like different sorts of AND gates, XOR gates, and whatnot, and that's
So you can create them, but you can create much more complex representations.
mm,
So these are just basic things you can create. But yeah, you can learn AND and OR and XOR through neural networks.
okay,
So XOR is actually impossible using just a single layer threshold neuron, but
right.
it's super possible if you add a second layer. I won't get into how you prove that's impossible, but I'll say it has to do with the fact that it produces a linear dependence. So let's go through backpropagation on a single neuron. So the network structure, we have one input x. We have a simple linear layer, w dot x plus b. So just a linear regression, no activation function, and mean squared error. So literally, this is just a linear regression here. And we're just performing backpropagation on linear regression. We'll get the same gradient as we would if we're taking the derivative with a linear regression. So we compute the gradient of the loss with respect to y hat. So that's 2 y hat minus y over n. I take the 2 in front, and then keep divided by n. And then gradient, so that's the gradient of the loss with respect to y hat. And then you take the gradient of y hat with respect to z. So notice we're just multiplying the gradients because we're doing chain rule. So we have the derivative of L with respect to y hat, and then we have the derivative of L with respect to z. And we have the derivative, we multiply that with the derivative of L with respect to W, or Z with respect to W. So we're just multiplying the gradients until we get the derivative of L with respect to W, which is 2 y hat minus y over n times x. And then derivative of L with respect to B is the derivative of L with respect to y hat times the derivative of y hat with respect to z times the derivative of z with respect to b. So that's just 2 times y hat minus y over n. So now that's a one-layer neural network. Just a simple linear regression that you're optimizing according to mean squared error. Then now let's look at a two-layer neural network. Now there are two inputs. There's a hidden layer with two neurons. So Z1 equals W11 times X dot X1 plus W21 dot X2 plus bias 2. And so now Z1, there's another layer. So there are two hidden layers. So there's Z1 and then Z2. So these are both different combinations of your original variables, and they're creating a combination which represents some feature of the data set. So a Z1 is a feature, and Z2 is a feature. And then Z3, now you're combining Z1 and Z2. So you take some function of Z1 and Z2, some activation function, and then that becomes A1. And then you're taking the dot product with W13, dot product with W23, and then plus a bias. And then you're doing the sigmoid activation function, which makes a probability. And then you're using binary process entropy loss because you're doing classification. So in this case, just all we're doing is we're creating one dimension, one feature. So we're combining features and we're into a dimension. So combining a set of features into a dimension, we're combining a set of other features into another dimension. We're taking a nonlinear activation function, and then we're combining the nonlinear activation function features with each other, and then we're converting them into probabilities. And then we're optimizing these weights, weight 1, weight 2, all these weights and this bias. You see how annoying this is? This isn't even like a 2-hour recitation. It's gone off twice. But yeah, so you're combining a set of features into dimensions, and you're taking activation functions of the dimensions, and then using those activation functions of the dimensions, you're combining them into another feature, which you're taking another nonlinear activation function of, and then you're using that as your prediction, and then you're optimizing that for your data. You compute the gradient of the loss with respect to y hat. You compute the gradient. Now you have dl dy hat, and then you do dy hat dz3, and then you do dz3 dwi3, and then d beta 3, and you just do it for all the different weights. So Hugging Face is an online repository of trained models that can be used out of the box or retrain. Hugging Face substantially reduces the time that we get into working with complex pre-training models. So I was younger and I first learned about neural networks. I'm not that old. I'm not nearly old enough to be saying things like when I was younger, but this area has moved so fast that I can say that because it used to be that if you wanted to use a neural network for something, you needed to code it yourself. But nowadays, you have these pre-trained out-of-the-box models you can just download through Hugging Face. You just do pip install transformers data evaluate. You just do pip install torch. Torch, by the way, will take the derivatives for you. You don't have to do any of those at gradient descent. Torch will take the gradient for you. It's crazy. And then you just import a pipeline. And look here, you can run GPT 2.5. You can run all these extensive pre-trained models with extensive weights on your personal machine. You just do front transformers, import pipeline, classifier equals pipeline sentiment analysis. And you can take BERT, which is a language model. You can take all these complex models and you can just run them on your machine. And then what's even crazier is with these models, once you've run them, you can find predictions and then you can alter them to train them again. So Hugging Face, I encourage you to, if you have a little bit of time, look into Hugging Face. I'll show you an implementation tonight if we get time. But look into Hugging Face, and there's so much powerful stuff you can do with these out-of-the-box models. Someone else took the time and trained it, and all you have to do is apply it. It's just incredible, and it's so fast, and it's dramatically reduced the amount of time it takes to get into machine learning, and just all sorts of models, computer vision, NLP, audio, all sorts of models on Hugging Face. It's a model repository. It's the best. And now with that, thank you so much. We're going to get into some code. Yeah, I know that tonight was kind of an intense PowerPoint. So we're going to get into some code here. So I'm going to start off with the logistic regression code. So I'm going to walk through the code and then I'm going to run it. So this code is kind of special because I'm doing logistic regression in several different ways. So first off, I import my packages. And I would encourage you, MD, and I encourage everyone following along in the recording, I encourage everyone to run this with me. Get your fingertips a little bit dirty. So I start by importing my packages and I create my data. And then just import the packages. And then create the data sets. You'll notice that the y's are all 1 and 0. And you'll notice that there are 2 variables for the x's. And then I have my sigmoid activation function. This is the function that returns a probability in a logistic regression, very common in neural networks. I have my log likelihood function. I take the dot product of x and the weights like I did before, and then I just do LL equals NP dot sum. You're doing it. This is code is what's called vectorized, which means I'm doing it straight with the vector. You never, never, never want to use for loop unless you can avoid it. If you can avoid using a for loop, do. Code runs so much faster if you're doing it in terms of matrices. So here I take the dot product of x with my weights, and then I do a sum of all the y's times the dot product of x with the weights minus np dot log 1 plus np dot exponential z. So this is that log likelihood we showed in the slides. And then if I add an intercept and we are tonight, we just do add another feature here that will effectively just add a 1 to each of the observation by matrix. So I'm just adding a vector of 1s. I'm just doing h stack to stack the vector on top of it. I'm initializing my weights to 0s. In logistic regression, it's okay to initialize your weights to 0s. Nothing's going to happen with it. But with something more complex like a neural network, you should really be randomly initializing your weights. And then here, I'm not choosing to have a condition of termination after it gets to a certain degree of closeness. I'm just taking a number of steps that's predetermined, and I am continuing to run the algorithm until all those steps have been taken. Hey, MD, what's going on?
So what does h stack mean there? We see x equals to np dot h stack interpret x. Oh,
Great
intercept x.
question. H stack means horizontal stack. So there are
Okay,
two types of stacks you can do in NumPy. One is V stack, which means I'm adding rows. One is H stack, which means I'm adding columns. So effectively what I'm doing here is adding a column of 1s. Great question.
Okay. Thank you.
So I take the dot product. I found the predictions. I find the gradient. I update the weights, and then if the step is a multiple of 1,000, I print the log likelihood. Otherwise, once we've gone through 10,000 steps, I'm going to return the weights. So let's see if this works. So yeah, it did 10,000 iterations just now. And as you notice, this is the cost function. Or this is the log likelihood function. We're maximizing it. We're increasing the log likelihood function. And we end up with these final weights. Now we can also do logistic regression with sklearn. So sklearn, if you'll recall, is a repository. It's a machine learning library. So all we do for fit a logistic regression, we do logistic regression. We can set a random state. We don't have to. And we do fit x and y. And then it will run for a second, and then it'll be run. And then, hey, what's up?
So I had another question. So as for the number of steps and the learning rate, how do you sort of determine that? Like, is it like something like how do you know how many steps should you do and what's the optimal learning rate?
So both of these are really a trial and error thing. The correct answer is do k-fold cross validation. But in reality, in both cases, what you need to do is try a series of steps and learning rates and look at you're gonna have what's called a loss curve. So loss curve is going to look something like this.
Mm-hmm.
And in in the best of all possible worlds, you're going to get a loss curve that looks like this, where it very quickly goes down and then it just remains kind of flat. If you have a loss curve that looks like that, you have the right learning rate and you have the right number of steps. If
Okay.
you have a loss curve that looks like, and then you stop right there,
Mm-hmm.
that's still a decreasing loss curve. That loss curve hasn't hit its bottom yet, so you need to increase the number of steps.
Ah, okay.
If you have a loss curve that looks like that loss curve is decreasing, but it's not decreasing very fast. You need to increase the learning rate.
Mm,
You need to make it go fast, Esther.
right.
If you have a loss curve that looks like that learning rate is out of control, you need to decrease the learning rate.
Got it.
So it's okay if a loss curve looks like this, because
Mm-hmm.
sometimes it will go up, particularly when you're doing stochastic gradient descent, but it shouldn't be all over the place. It shouldn't be going up and then down. If that's happening, you know the learning rate is too low. So really, I encourage you, I don't plot a loss curve here, but
Mm-hmm.
really I encourage you to plot a loss curve, look at what's going on with this log likelihood,
Mm-hmm.
and that will tell you what's going on with your steps and step size and number of steps.
Got it.
You'll notice here at the beginning it's decreasing a lot.
Mm-hmm.
Goes from -6 to -0.51. It's increasing a lot, rather. It's maximizing. It's increasing a lot. Right here, it's increasing a lot. And at the end, it's not doing anything. So that suggests that it's doing what it's supposed to. If you plotted that, that would look like a good loss curve.
Got it. Got it. Thank you.
So, and then I can also, so I fit the logistic regression, and now I can also predict the value. I can predict, so it predicts ones for those two. So, if you notice, so let's see, I did the first two, those both were ones. So it was 1 and 1, so it correctly predicted those. I can also predict the probabilities of those two. So it will be greater than 50% in this case because it predicted ones, because the decision rule here is predict ones. So this is the predicted probability of those two. And then I can also do the score, which tells you basically the log likelihood, which is 1. It's a really high likelihood because I'm effectively matching everything in this case, because it's a very simple case. And so this is the third way we're going to do logistic regression tonight, and this is through PyTorch. PyTorch is the dominant way to train a neural network. And so the way you do it is you do a class, and then you do your type of model, and then you do neural network.module, and then you define your layers. Here we only have one layer in our forward pass, and we do self.linear equals neural network.linear. So it's one linear layer because of logistic regression. Remember how I said logistic regression, neural network, same thing at a very basic level? That's what I'm talking about here. So forward pass, we just do a linear layer, and then we do a sigmoid activation function. So that's all this PyTorch linear logistic regression is. And then we train it. So for a number of epochs, for a number of steps, we train the model. We convert to tensors, and then we do gradient descent. So we do the forward pass, outputs equals model of inputs. We take the loss, and then we do loss dot backwards. So what backward does is it does all of gradient descent by itself. That's what's so powerful about PyTorch is it automates the process of finding the derivative. And then this optimizer.step, that's the gradient descent. So here it finds the gradient. Here it takes a step in the direction of the gradient. So here I define this as the model. So this all here is defined as the model. And then model has an input dimension. I'm telling it that this is how many inputs this has, which means this is how many variables the model will take. So I'm telling it that this has two variables. There's two variables in this case, plus a bias, which the model add itself. And then create a logistic regression. I do criterion equals binary cross entropy loss. That's that log likelihood function. Our criterion is a log likelihood function. And then our optimizer, we're going to do stochastic gradient descent with a learning rate of 0.01. Like I said, you can choose this via A-means cross validation, or you can choose this by looking at the loss curve. Choose a number of epochs. We train the model, and then we print the weights. So now we're just going to run this. I really appreciate you coming, MD, because it's great having people can ask questions. I love to hear any question you might have. So it's just going to create an optimizer, create the model. It's going to train the model. So right now it's in the middle of training, and it'll train 10,000 epochs. And notice, if you will, that the log likelihood is effectively the same as before. It's just now this is before it was a log likelihood, and now it's a cross entropy loss that's positive. And now here are the weights. Also, the weights before we had something that was relatively similar, I would say. And then now we can do it on this data set called the iris, which is a very classic, simple data set in data science. And we just run all three logistic regressions on the iris, and now we'll have another trained logistic regression data set. So that's three different ways to do logistic regression. The first is by coding it yourself, and then we even coded the gradient descent step ourselves, which was not hard in this case. The second is by using sklearn, and the third is by using PyTorch. So that's logistic regression, and then I'll give you a moment to ask any questions, and then I'll show you some other code.
I had some questions unrelated the class today. It was about the
Sure.
previous class, like how you mentioned like the different data like sources of data that we can go to. So like FRED or like the IRS or like the Census Bureau, right?
Yeah.
So I was going through like the different websites, but I was struggling to sort of find data sets or like get data sets. I was wondering if you could show like how to get data sets from there. Just a quick
Okay.
example.
Sure.
Because I was like trying to navigate through the website to like see where the data sets are, but I just couldn't find it at all.
So I got Census Bureau data. So it's easier. Do you have a topic you're interested in a data on?
So let's say I want to do like housing price and analysis for New York. Let's just say that.
Okay. So the Federal Housing Finance Agency will have some data on this.
Mm-hmm.
And then we download CSV format, and then we get something that's going to look a little bit messy.
Right.
And then we have to, it's not that messy. So here we have the housing indexes,
Right.
and we can compare for different cities. Now that's like very broad data. I don't know if you
Right.
noticed, but that's like very 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 broad, not specific data. So really, Zillow has a really great housing price data.
Interesting. Okay.
So Zillow releases data on housing prices and also features of housing.
Mm.
So I can go to New York. I can download this at different levels, and I can get data over time on the price of houses by different features of houses.
Ah, okay, 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 okay.
And this allows you to create what's called a hedonistic regression, which provides, let's see what it looks like if I download it. I think it's going to take too long, but let's see. Oh, it was fast. But let's see what it looks like. But yeah, you'll get something by state, and you can also get something by houses, and you can
Oh,
get
goodness me.
for different variables. You can get for sale listings, rentals, home value forecasts, home values. You can get a data set with houses when they sell, and yeah. So Zillow housing. Let's try sales data. So yeah, you can get housing data from Zillow, and there are other housing sales data sets.
And on the topic of data, would you mind, so because you have like work experience, would you mind sharing what type of projects to do, like or like the projects that you would do if you were to like sort of do machine learning or data science?
So that's a great question. If I were trying to get into machine learning right now, I think what I would probably say is a very useful project
Mm-hmm.
is so first off, obviously it depends on what your interests are,
Right.
but I would create a data pipeline.
A data pipeline.
I would start by so there are a couple of different types of projects I would do.
Mm-hmm.
First, I would create a data pipeline, which
Right.
means I would find an API somewhere,
Uh-huh.
and I would get a way to automatically download the data. Then I would clean the data automatically. So you're doing this all in R Python. You're automatically getting the data, you're automatically cleaning the data,
Mm-hmm.
and then you're performing some analysis on it. Because that's what companies really want you to be able to expect you to do is get data automatically and then automatically clean it. So that's one thing I would do.
Mm-hmm.
So let me show you something. It's something I spent a lot of time doing, and I was really proud of it when I did it. Actually, the code for this is on the course website. I think it's attached to the first week. Uh,
Really? Oh, the API call thing?
yeah.
Ah, okay, okay, okay.
AKI calls SEC. Everything here is actually something that you could do with a little bit of practice.
Mm-hmm.
It's really time consuming because it takes a while to like actually build it out. But
Right.
basically what I do here is let's real quick walk through this code. Um, I load in some names of tickers, and I load in some names of companies. I create a blank data frame, and I iterate through the companies. And I using this sec-api.io, and this is a free API. It's expensive if you're querying it all the time, but for just a few queries, it's free. So this is sec-api.io. So this is an API that you can query. And so first off, I use the API, sec-api.io.api. I query it to get what's called the kick code. So this is an identifier code the SEC uses. And so this allows me to standardize my data set with what's in the 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 API that I'm querying. And then I send it a query looking for all the forms that might be published by a company. So to give you a sense of what these forms kind of look like, um, so so to give you a sense for what these forms kind of look like, we go to the folder where I have them. Work with Ava. And then data, and then very next tab. This is the wrong one. And then I go to Phonodocs 1995. So these are a bunch of forms that companies actually filed. And so I'm automatically looking for the forms, and then I'm downloading the forms and I'm extracting information.
Oh.
So the API will extract, if it's an 8K, it will, or sorry, if it's an 8K, it will extract for me the text I'm looking for. So this is called the extractor API, your API URL. It extracts item 5-7, which is the item I'm looking for. And then if it's not an 8K, I use what's called a regular expression to search for the text I'm looking for. And so then I get the text on voting from the document. I get it for 8Ks, I get it for 10Qs, I get it for 10Ks. And then this is where the real magic is. Now I've got some text, and it's really kind of hard to decipher for the computer. It's very easy for me to read, but I can't like read it thousands upon thousands of times.
Right.
So here I do this magic where I work with ChatGPT's API. So ChatGPT also has an API, and I send ChatGPT a query explaining what I want to do, and I send it to the text, and it sends me back
No way.
a CSV. And so I go from thousands upon thousands of documents to a clean, relatively clean, a clean CSV with all the voting records of different companies.
No way.
Yeah.
That's sick.
So nothing in that was all that technically difficult. I'm not even writing my own AI. I am querying someone else's AI. But the challenge is you have to figure out a lot of very specific things about how all this works.
Right.
That's the kind of project that I think is very valuable, is building a data pipeline to answer a question. It's come with a research question that can be answered using some data in a data pipeline. Census has APIs, Fred has APIs, and then build a pipeline that will automatically download, clean, and analyze the data.
That was very I think it was a very rigorous project.
Thank you.
Like I especially I really like how you use ChatGPT API to like write a command to ChatGPT in code. That I didn't know you could do that. That's so sick.
Yeah.
Yeah, that's pretty cool. That's pretty cool. Oh, I guess
Um.
that is the end of class.
Yeah, I was gonna get into some. Do you want to see some neural network code?
Uh,
You can look into it on your own time. Let me dismiss you, and if you want to, there's some neural network code also in today's class.
okay, yeah, I'll look into that.
All right. I hope you have a great day.
Thank you, you too. Bye bye.